So in this video, I will try to explain what Stokes' theorem is telling you from an intuitive point of view. So what is it in a mathematical sense first? Well, this is the formula. And if we look on the left-hand side of the equation, it essentially says that for a closed loop, all it's doing is adding a vector field across the loop's length at each infinitesimally small segment across the loop. It adds up the vector field pointing in the same direction as the loop. This ends up giving you a numerical scalar value. Right? So it stops becoming a vector and becomes a scalar. Now for the other side of the equation, what we have here is essentially saying the curl summed up across this entire surface bounded within the loop. So let's say everything within here is equal to that numerical value. Now, how is this? First, we have to understand what curl is even talking about. So curl is defined as the amount of vector field rotation happening over an infinitesimally small area. Curl is the amount of vector field rotation happening within this entire surface that's closed within the loop. And one thing about curl is that it points, the vector of curl itself points in a direction that is perpendicular to the surface. Always. Similar to how in Gauss's law, the electric field points in the direction of the infinitesimally small area, curl has a vector field, has a vector that points perpendicular to its rotation. When we add up all the rotations within this surface, we would find out that the shared edges eventually contribute to zero vector field and essentially cancel out. So in the end, across the entire surface, all vector fields contribute to net zero, except for the little curl, for the little rotation, should I say, happening across the outermost edge, also known as the loop itself, of a wire or conductor. And that is Stokes' law.